Welcome to Math You Need for Machine Learning. This is the first episode in a series that will teach you key concepts in math techniques for machine learning. Machine learning is a relatively new field where things are still evolving and are far from solved. It's completely normal to feel lost by the math. But learning the intuition behind machine learning and why it really works is one of the most satisfying paths you can take. So I want to share this journey with you where we'll work with tangible examples to see what's going on beneath the hood. Let's begin. The first topic we're covering is gradient descent, which is one of the most important ingredients of machine learning. Gradient descent is the gradual process of adjusting the parameters of a model so that it improves. In this animation, we're watching the embeddings of a model evolve over time. As the training process continues, the words begin to cluster, and we can trace the loss going down. For any machine learning algorithm, there is always an objective we want to optimize. On the right side, we have the objective of a model, which is to make correct predictions given inputs. We want to maximize this objective. On the left side, we've reframed things in terms of loss. Minimizing the loss is the same thing as maximizing the objective. We call the process of adjusting parameters either gradient descent or gradient ascent. It really just depends which perspective you want to take, but in all cases, we're making things better. In this video, we'll actually be performing gradient ascent by increasing the probabilities of correct predictions, but the underlying math is just the same. To appreciate the math behind this, we're going to take a look at the Word2Vec model and learn how to calculate its gradient. In turn, we'll understand the true nature of how the embeddings are shifting over time in this animation. The math you learned today shows up in all types of other machine learning models. Some of my favorite examples include reward models, which are used to improve large language models, ELO ranking systems, which are used for rating players in games like chess, and image classifiers, which can help us scan and automatically label images. In a previous video, I walked through how people came up with Word2Vec, but one thing I didn't cover is the gradient. And that's because modern deep learning libraries usually take care of this for you. You can simply just ask your favorite library to figure out what the gradient is, and then make a step in that direction. But sometimes it's equally important to see the math come to life and really understand what's going on. So that's what we'll get up to today. To start out, we need to define the Word2Vec model. The goal of Word2Vec is to distinguish between real word pairs that came from a sentence in our dataset and fake word pairs that were sampled at random. For example, the first pair here came from a sentence, so we want our Word2Vec model to classify the pair as real. Meanwhile, the bottom pair was formed by randomly sampling from our vocabulary. We want our Word2Vec model to classify that pair as fake. The parameters of the model are stored in tables. Each word has a unique vector associated with it called an embedding. To get the embedding for a word, you just have to look up its entry in the table. In Word2Vec, there are actually two embedding tables. So each word in the vocabulary has both an input embedding, which we denote with a V, and an output embedding, which we denote with a Z. To classify the relationship between words, Word2Vec first measures the similarity between their word embeddings based on the dot product. The model then uses the sigmoid to make classifications. As a refresher, when the inputs to the sigmoid become large, the sigmoid approaches 1. When the inputs become very negative, the sigmoid approaches 0. Intuitively, Word2Vec will classify words as real pairs if their vector similarity is high. Altogether, we have the following. According to the Word2Vec model, the probability that an input word T is real neighbors with a word N is the sigmoid of their vector similarity. The higher the similarity of the pair, the more the model thinks these two words are a real pair. Meanwhile, the probability that an input word is not actually neighbors with another word is just 1 minus the probability that they're real. If any of that felt confusing, I encourage you to check out the previous video where we worked through everything we just discussed in detail. We talked about embeddings, vector similarities, the sigmoid function, and why Word2Vec even does this classification to begin with. But moving on, it's time to now define the objective we'll be maximizing. The goal of Word2Vec is to maximize probabilities. When we provide an example data point as an input to the model, we want predictions from the model to match the correct label for that example. More generally, when we're talking about objectives for machine learning models, we're optimizing over the whole training dataset. We don't just want one prediction to be perfect. What's happening here is that we're multiplying together all the probabilities for each of the examples in the training dataset. One intuitive reason we do this is that if we perform poorly on any of the data points, then the whole product will get dragged down. This can prevent our optimization from entirely ignoring pockets of our data out of convenience. There are deeper theoretical reasons for why we do this, but we'll have to save it for next time. A commonly performed transformation is taking the logarithm of our objective. Here's an example of what happens when we apply the logarithm. As we can see, each of the multiplied probabilities split into a sum. It's okay to take the logarithm of our objective because the logarithm preserves the order of numbers. If we optimize log probabilities, we also optimize the original probabilities. One practical reason we take the logarithm is that it has a nice property of distributing a product into a sum. This is going to make taking derivatives a lot easier, which is what gradient descent is all about. So finally, it's this sum of log probabilities that is used as the Word2Vec objective. Let's walk through how we get from the top to the bottom. For Word2Vec, the inputs are pairs of words to be classified. The labels are whether the pairs are real or fake. And lastly, the sum has just been split into two cases based on their label. Altogether, the objective of Word2Vec says, maximize the probability of correctly classifying real pairs as real, and maximize the probability of classifying fake pairs as fake. For each word T, we'll sum across its neighbors obtained from a sentence, and also across a set of randomly sampled words. A better model will be more likely to predict the right outcome for different word pairs. Congratulations for making it this far. That was already a lot of information, and you can always go back through it with the lecture notes, which can be found in the video description. But stay with me for now, because it's time to get training. When we begin training our model, the input and output embeddings for each word will be completely random. It's actually quite important how we start things out. In some sense, we want to be strategic about our randomness. We call this the initialization of the parameters. One common choice is to initialize the vectors using a standard normal distribution. For each vector, each of the components is a random number sampled from the normal distribution. How do we know if this is a good choice or not? Well, let's say our embeddings are 100-dimensional, meaning each word is assigned 100 random numbers to start out with. If we looked at the distribution of the dot products between these random vectors, we would see something like this. As we expect from completely random vectors, their average similarity is 0. Meanwhile, the variance of their dot product is approximately the dimension of the vectors, which in this case is 100. If we were to take the sigmoid of these similarities, we would see strange spikes like this. This represents the untrained model's probabilities. This is a moment to emphasize that it's important to look at the distribution of various quantities in your machine learning algorithm. It's going to be painful for this model to learn if it's already so confident about its predictions before it's even started. So let's fix this by dividing by the square root of the embedding dimension. Now, the initial distribution for predictions looks great. Most of the predictions are uncertain. That is, they're near the center, around a 50-50 chance. For those of you that are interested in why this works, I'll leave a short proof in the lecture notes. Taking this further, we can actually bundle the rescaling into the initialization of the vectors. Sampling from a normal distribution with a smaller range of values will make sure similarities don't blow up at the beginning. Now we're in good shape. All right, it's time for the gradient. Everything we need to prove will boil down to these two cases. Intuitively, we know that real pairs should get closer and fake pairs should repel each other. But can we prove this? Let's get to work. We're going to calculate the gradient in 3 main steps. The first will be figuring out the derivative of the sigmoid. The second step will be defining what a gradient even is. The third part will connect it all together with the chain rule. As our first goal, let's focus on the logarithm of the sigmoid. First, we'll rewrite things using the properties of the logarithm. Now it's time to take the derivative. The first term is nice and easy. The derivative of x is 1. The second term involves a logarithm of a function, which, by the chain rule, is 1 divided by the inner function times the derivative of that inner function. Spend a moment proving this to yourself. Finally, we can collect terms by putting them all under the same denominator. Putting this in one line, we've already proved something quite nice. Perhaps you'll notice something going on. As a refresher, here's what we learned last time about the sigmoid. Its complement has a very simple form. And if we use this fact, we'll see that we have already proven a pretty interesting relationship. We'll talk more about the interpretation of this later, but this is a huge step forward towards our sought-after gradient. Next up, let's refresh our memory on the chain rule. To compute this derivative, we can first take the derivative of the outer function with respect to f, and then multiply by the derivative of f with respect to x. Let's fill in the derivative of the first factor using what we just learned. The derivative of the log sigmoid with respect to its input f is just 1 minus the sigmoid of f. If this looks sketchy to you, then it's a good time to get out your pen and paper with a reference to the chain rule handy. Now, stay with me here. What we just proved works for any function, and the dot product between z and v is also a function, so we can apply the chain rule in just the same way. If this is your first time thinking about functions of vectors, this might feel really weird. So let's work out the details together to figure out what just happened. Let's start off with what we gathered a moment ago from the chain rule. Then we'll make the following substitutions. We'll substitute x with v1, the first component of v, and for our function, we'll choose the dot product between v and z. Let's assume for simplicity that z and v are 3-dimensional vectors. Then, when we work out the dot product between z and v, we get a simple sum involving the vector components. We see that f, which is the dot product, is a valid function. So it's appropriate to use the chain rule like any other function you've seen before. In fact, if we ignored the other vector components of v by holding them fixed, then we see that the dot product is simply a linear function of v1. It makes sense. If we slightly nudge the value of v1, then the value of the dot product will increase linearly by a scaling factor of z1. What we're doing is called taking the partial derivative of a function. The partial derivative expresses that we're just focusing on how the dot product changes with respect to v1 while keeping everything else fixed. Pretty neat, right? You can repeat this process of taking the partial derivative for each of the vector components of v. Altogether, we get a pretty clean pattern. And if we stack the partial derivatives together into a vector, we form what's called the gradient. So we've proven that the gradient of z dot v with respect to v is just z. Honestly, this is pretty cool in its own right. If this is your first time seeing the gradient, in the most basic sense, it's an organized collection of all the partial derivatives of a function. In terms of optimization of our Word2Vec model, It stores all of the different changes we would want to make to our embeddings in order to improve predictions. The gradient is the generalization of the derivative for functions with multiple inputs. For instance, this function here has two inputs, x and y, and the function's value is colored from purple to yellow. To climb up this landscape, we can follow the gradients, which are annotated with arrows. In machine learning, the same picture is going on, but in much higher dimensional space. At each step during training, we're figuring out what way our gradient arrow points. We'll then move that way, repeating this strategy over and over until we're happy. In this picture, the path is going downhill, which means the algorithm is trying to minimize losses. This would be called gradient descent. If we flip the picture and we're climbing uphill, we would call it gradient ascent. Recapping, we now have all the key facts we need to derive the gradient for Word2Vec. Everything we've shown with the vectors generalizes to higher dimensions, but I think it's just easier to list out a few dimensions and see what's going on. When in doubt, if you're confused about taking derivatives with vectors, I recommend you write things out in 1D, 2D, or 3D, and try to get a feel for what's going on. Okay, to bring it all together, let's write out the chain rule from before, now for all of the vector components. So here, we've just applied the same chain rule for each component. We can rewrite the same equations in vector form, which is much more compact. Once again, the gradient is just collecting all the partial derivatives from each of the components of V. A lot of the confusion around the math of machine learning is due to vector notation. A lot of what we've shown so far for each of the components is quite reasonable, but when we start to stack it together, it looks alien to us, at least at first. Once you get used to this notation, you'll realize that it's mostly bookkeeping, and what's going on in each dimension is really reasonable. Okay, so the last step here is just to fill in the gradient on the right side. And if we use our handy new relationship for the gradient of the dot product, we have officially proven the gradient for Word2Vec. That's pretty awesome. And now we're going to interpret the meaning of this gradient. First, let's fill in all the Word2Vec notation. We have a current word t and its real neighbor n. We're studying the gradient of the log probability with respect to the current word t. We have just proven that the gradient of this log probability is as follows. And notice that the gradient points towards the neighboring word. If we nudge our current word t towards the neighboring word, we'll increase the probability in the future of classifying them correctly as real neighbors. And meanwhile, there's also a factor that scales the gradient up and down from 0% to 100%. It's 1 minus the sigmoid of the vector similarities. And by now, we know what to do with this. This is just the probability that the pair is fake according to the model. Something amazing is going on. To update the embedding for the current word, we'll add some of the neighboring word to it. But we'll stop doing this once we already know this information, as encoded by the p-fake scaling factor, which will decay to 0 as the model becomes confident that the pair is indeed real. In general, making classifications with the sigmoid has a very beautiful property, which is that it's self-balancing. If the model already knows about the relationship between a pair of words, then no more learning needs to occur, and the model can instead focus on less certain word pairs in the dataset. You can think of this physically as forces between words. At first, words are randomly scattered. Nearby words that are unrelated will repel. Meanwhile, words will attract to their real pairs until they settle close enough to each other. As things move around, words will interact, and ultimately, things will come to a balance as we decay our learning rate. A similar thing happens for fake pairs. The current word will move away from the vector of the random word, with the force decaying once this information is already known to the model. We now have a mathematical description of Word2Vec. Real neighbors attract, with the attraction decaying when they're already close enough. Fake neighbors repel, with a force that weakens when they are far enough. I find the self-balancing nature of Word2Vec absolutely beautiful. To wrap up, I want to link things together. The math you just learned applies all over the place in machine learning. In logistic regression, classifications are made based on a linear function inside the sigmoid. Each input is linearly combined with different weights to determine a raw score. Finally, this score gets passed into the sigmoid classifier to make a prediction. Likewise, ELO rating systems also use the sigmoid, but written with powers of 10 instead of E. The probability that one player will beat another is based on the sigmoid of their ratings. If a player has a higher ELO than another, the model predicts that they're more likely to win. After a game takes place between two players, the update to their ELOs is made based on the gradient that comes from the sigmoid. The self-balancing of the sigmoid makes sure that if you're new to the game and you lose an unbalanced match to a masterful player, then there's really nothing learned at all, and your ratings will mostly stay untouched. Another example of the sigmoid in action is reward models, which are a critical component for making large language models able to chat with people. Reward models read in a conversation consisting of a prompt and a response. The job of the reward model is to score the quality of the response. The sigmoid of the difference of their scores is used to make predictions about which response is better, kind of like an ELO rating but for language. We'll dive into this exact model in the future. Another very recent example that's been trending in the large language model space is direct preference optimization, or DPO. The authors highlight self-balancing in their analysis of DPO's gradient. In all these applications, the self-balancing nature of the sigmoid is always behind the scenes. We're going to stop here for now, but you can look forward to more math to come. If you're excited to see the rest of the series for math you need for machine learning, please show your support by liking this video and be sure to stay tuned by subscribing. Thanks for listening, and I'll catch you in the next video.